Welcome back to che531. In this video, I'll be showing you one example of an optimization problem where we want to maximize an objective function. So the objective function is basically something like this: 5 times x1 plus 3x2 plus x3, and that is subject to 3 constraints. Well, 2 constraints plus the non-negativity. If you want to do this in MATLAB, you have to note that in MATLAB everything is about minimization, and if you have a maximization problem, you have to convert that into a minimization problem. And as we discussed this in class, to do so, we've got to multiply the objective function by negative sign and convert it to a minimization problem. Like if I multiply this by negative sign, then minus 5x1 minus 3x2 minus x1 needs to be minimized. And then in MATLAB, I have to put the coefficients accordingly. Like I'm going to put minus 5, minus 3, minus 1 for f, right, corresponding to these three, right, minus 5, minus 3, minus 1. And then I have 2 constraints. I put them into the A and B matrices, right? So B is the right-hand side, 6 and 15, and A is like 1, 5 first column, 1, 3 second column, and 1, 6 third column. Okay, I do not have an upper bound. I only have a lower bound for my variables. Lower bound is just all of them bigger than 0. And there's no equality constraints. I'm going to put them as a blank matrix. Put them all into a lin-prog function. And I'm going to use dual simplex. You run it, and what you get is, well, you get a solution. And let's say this is one solution. And you look at the function itself, you see it's minus 15. Now, we minimize the function, so this is the minimum. That means, go back to the original problem, minus 5x1 minus 3x2 minus x3 is bigger than or equal to minus 15, right? Because we minimized it. So this is the minimum. You can multiply through by negative sign, then you get 5x1 plus 3x2 plus x3 is less than or equal to 15. So now this is the maximization problem. So the result will be 15, the negative of what we get. You have to multiply this by negative sign because we multiplied the original problem by a negative sign to convert maximization to minimization. And that is because MATLAB only runs minimization problems. MATLAB cannot do maximization, just to keep that in mind when you do MATLAB. Okay, so I hope this is useful. This is basically related to one of the homework problems that is due this week. All right. In the rest of this video, I'll be talking about another algorithm that can be used for optimization. So far we talked about linear programming, means everything is linear, the objective function is linear, the constraints are linear. But that is usually not the case. Most of the time we have nonlinear objective function or we have nonlinear constraints. So the simplest case would be we just look at nonlinear objective function and assume that the problem is unconstrained optimization. That means we do not have any constraint. I mean, just for the sake of simplicity, we only bring in the nonlinearity to the objective function. And once we find that out, then we can go ahead and add the nonlinearity to the constraints. So, so for now, we're going to focus on only nonlinear optimizations where we have nonlinearity in the objective function. We do not have any constraints for now, so let's call it unconstrained optimization. Okay, so the first method we're going to look at for unconstrained nonlinear optimization is called steepest descent method. And the name is actually coming from a very natural phenomena that maybe you've been out there and maybe you've gone for hiking or something like that. So imagine, like we have an image of this valley. So there's a valley here and we have mountains around it, right? And so I'm going to go and ask a question that, let's say if we get rainfall here, and I'm just looking at one of the, or maybe just look at a raindrop, and ask if I leave or drop, some water right on top of this hill, how does it actually get to the bottom of this valley, let's say here? So from here, we will have to see how nature actually treats water drops, or rainfall, to basically direct water flow from here to here. So you may think, there are a lot of paths, but let's say one path could be maybe from here it just goes along, the highest points up to here and then directly down to this point. This is one way. Another is maybe it directly goes down from this point to the bottom of the valley there, and then from there to here, which may not be able to actually get here, because if there's another small uphill between, let's say, that valley and this valley, then it cannot actually go up. So we know that water cannot go up. So yeah, so the question is how really physics, leads water drops, from top of the mountain to the valleys. And this is basically the algorithm we're going to follow. So part of this mechanism in nature actually is driven by what is called steepest descent. So water is actually going to go along the steepest descent direction locally. That means at every point it looks for the steepest direction, and then it takes that direction and it goes until it finds a better, or maybe another steep direction close by, and then we're going to switch to that and so forth. So pictorially, if you want to show this, it's something like this. Let's say we have a mountain here, we have a bunch of valleys here, and we ask a question, if I start from here, how I get maybe to this valley. So we're going to go first with the steepest descent direction along this dashed line until we hit, let's say, point B. At point B, the steepest descent is not along this AB vector. It's going to be along now BC vector. So at some point we have to change the direction. Okay, so this steepest descent is not just we get one direction and go all the way down. We have to just search every now and then to find other steepest direction that is locally actually steepest, right? So this BC is locally steepest at point B, and AB is steepest at point A. So we see that the steepest direction changes as we move along this manifold, right? Okay, so with this idea, we're going to go and mathematically put down the equations that we actually can solve and find the minimum of the objective function. Imagine this is the 3D visualization of the objective function. Okay, so objective function can sometimes be high, can sometimes be low, and maybe the lowest. Locally could be high too. And if you start with initial guess, let's say at point A, the question is how do you really minimize the objective function to get to the minimum right here? Okay, so you see the path is not really straight, so maybe you have to go to point B, and then maybe from B to another point here, let's say D, and then from D to maybe E. And if you don't choose the right direction, you may go from A to B to C, and C is not really the global minimum, but local minimum. Okay, so you see that the path is really important, because sometimes we may reach the local minimum and not really the global. Okay, so the steepest descent direction that we're going to follow actually does not lead to global minimum. Almost all of the non-linearization or nonlinear optimization algorithms that we're going to look at is basically searching for local minimum. They never reach to the global minimum. to get the global minimum, we have to start with multiple initial guesses. Like if I start with this initial guess, it leads to this local minimum. If I choose another initial guess, let's say right here, I may, get to the other local minimum, and this local minimum compared to that one actually is global. So you basically throw out a bunch of random guesses along this, 2D plane or 3D surface, and then start from there using steepest descent direction or steepest descent algorithm to find the local minimum from which we find the global minimum. I mean, if you have a bunch of local minima, then the global minimum would be the minimum of all global minima. Well, the minimum of all local minima would be the global minimum. Okay, so knowing how to get the local minimum is important. And the first method we're going to look at is called steepest descent. This is by reminding us that we're going to follow the steepest direction, and then every few steps, maybe every few iterations or something like that, you have to correct the direction. So we need two major steps. One is choose the direction, and second is correct the direction. Okay, so mathematically, if you want to minimize a function like f, so this f is a function of initial guess x, and also a function of the direction that we have to choose. Well, x is not difficult. I mean, you can start with any guess. I mean, I don't think guess is really difficult. But the difficulty comes to choosing the direction. Now, which direction we have to choose? We just said there has to be steepest descent direction. And to get the steepest descent, what we do is we get the gradient of the objective function. So imagine this is the objective function in 2D. So imagine we have x1 and x2, only two variables, and objective function is a function of x1 and x2, which can be cast in a vector form like x. All right, so in 2D, the function looks like this, like a curve. Now, geometrically, gradient is a vector, right? So gradient of a scalar function is a vector, and that vector is represented by this arrow here, which is always perpendicular to the curve at the point that we calculate the gradient. So if I go ahead and calculate the gradient here, it's going to be a vector perpendicular to the curve right at this point. Now, there are two directions, going up or going down. So which direction is the gradient direction? I know I know it's along the perpendicular direction, but along this line of perpendicular direction, I have two ways to go. Either go to the top or go to the bottom. So which side is the gradient? Well, by definition, gradient is in the direction that the function increases. So if the function increases this way, so like this f, let's say, is smaller than, I think I have to draw a line or something like that. Okay, so let me just draw a line. And let's say here is another line. And here is another line. And here is another line. So these are actually four different values of the objective function. Imagine I put in different x1 and x2 in my objective function here. And for every x1 and x2, you get an f. Let's say this is a contour line along which f is constant. Now if I change my x1 and x2 to get another f value which has a higher value than the original one, then I get this curve. So basically the function value goes up, let's say, along these curves. Like this f is smaller than this, and this f is smaller than that, and that f is smaller than that. If this is the direction that f is increasing, then the gradient is basically along this direction, but perpendicular to all of them. So the point is, gradient is always in the direction that the function is increasing. Okay? With the same token, we can say the negative of the gradient will be the direction that the function is always decreasing. So now we get the steepest descent direction. It's going to be negative of the gradient. Okay. All right, so stay tuned on the next part of nonlinear optimization. Thanks a lot for watching.